So now let's look into the first example. Right, so we have a beam with the cross section shown below is loaded with a uniformly distributed load of 30 kilonewton per meter, okay, with the E value of 250 kilonewton per millimeter square. Right, so calculate the maximum bending stress in the beam, okay, and also the moment of resistance of the beam at the bending stress of 165 newton per millimeter square. Right, so as for the first question, okay, you are required to determine, okay, the value of sigma maximum, okay, and as for the second question, okay, you are required to determine the maximum moment of resistance. Okay, so one is that you have to determine the value of sigma, okay, and another one is that you have to determine the value of m. Okay, right, so given here, okay, are the loads, okay, that you are required to have. Okay, then we have the UDL, okay, which is 30 kilonewton per meter. Okay, and we also have the um, distance, okay, between between support A and also support B. Okay, and we are having an overhanging beam here, right? Okay, so and you are also given the cross section of the beam. Okay, so it is an I beam, okay, with the dimension that is given in the figure. Okay, then now we are going to look into the solution. Right, so as you can see here, okay, since we have a beam with only the loadings given, right, so therefore what you have to do first is to calculate the reactions. Okay, so we will start with the calculation of the reactions, and the values of reactions are RAY of 56.25 and RBY is 93.75. Alright, so since we are going to determine the value of the bending stress, therefore we are required to have the value of the bending moment. Right, so we can determine it the maximum value of the bending moment, okay, since we are required to determine the value of sigma max. Right, so sigma max, okay, is in relation, okay, to the moment maximum. Right, so therefore we need to determine the moment maximum value first, okay, then only we can proceed with the next calculation. Right, so you can see here, okay, in this calculation it is shown here that the value of the moment maximum is given as 52.73 kilonewton meter, right? So you can calculate the value, okay, using the knowledge, okay, on the bending moment diagram as what we have discussed earlier, right? So this is for the solution, right? Okay, so then now, okay, we are going to calculate for the moment of inertia, right? So as what I have mentioned earlier, right? So we have the equation of sigma equals to my over I, right? So we have already determined the value of the moment. Okay, so now we have to determine the value of the moment of inertia, right? So to fill up in the equation, right? So as for the moment of inertia, right? So since as for this section, okay, it is a symmetrical section on top and bottom as well as for the left and right. Right, so you can see that the value of the moment of inertia can be calculated using this equation. Right, so we are going to calculate the total moment of inertia, okay, for the section. Then we are going to deduct by these two moment of inertia for these two areas. Right, however, this method is only applicable if we are having a symmetrical section. If it is not a symmetrical section, therefore you are going to have to use the equation, okay, that is using the um, values, okay, of area, okay, as well as for the distance to the centroid. Right? So here, okay, we have the calculation for the maximum bending stress. Okay, since we have already determined the value of the bending moment, okay, as well as the value I, okay, which is the moment of inertia. Right? So therefore, we are going to have to calculate the value Y. Right? So as for this value Y, okay, it will be considering the centroid of our section. Right? So as for the centroid of our section, okay, since this is a symmetrical beam, okay, symmetrical I-beam. So therefore, the height of this beam will be divided by 2, right? So as you can see here in the figure, right? So we have a total um, height here, okay, of 20 plus with 20. then plus with 175, right? So therefore this h, okay, can be divided by 2, right? So therefore we have h over 2 here and also h over 2 here, right? So we have the value of 107.5 okay, for the top and also bottom, right? And as for this beam, right? So since we know that, okay, our beam here, okay, is a beam that is going to bend downwards, okay, within the area of the maximum moment, right? So therefore, we are going to consider, okay, the bending moment diagram that looks like this, right? Okay, so we have a beam, okay, that is subjected to UDL, okay, and then we have the support, okay, at A and also support B, right? So we have support A and also we have support B, right? So here, okay, you can draw, okay, the bending moment diagram, right? So the expected bending moment diagram will look like this, okay, whereas it will bend downwards within this section and it will bend upwards at the support, okay, and it will end up like this, right? So these blue lines, okay, are the bending moment diagram lines, okay, whereas you can see that this part will be positive and this part will be negative, okay, right? So and as for the bending maximum bending moment, okay, that we have determined earlier, right? So it is located here, right? So it is here, okay, so this is the maximum moment, right? So therefore, okay, for this type of um, behavior, okay, whereas our beam deflects downwards, so we know that the bottom part of the beam, okay, will be subjected to tension, right? So since we are going to have our beam bending downwards, so the bottom part will be subjected to tension and the top part will be subjected to compression, right? So therefore, when we calculate, okay, the value of the maximum bending stress, okay, so we know that the bottom part is positive and the top part is negative, right? Okay, so here what we are going to calculate, okay, is the value of sigma maximum, right? So therefore we have m, okay, times with c, right? So as for this example, it is using c, okay, but it is actually similar to y, right? Then divide this by I, right? So we have 52.73 times with 10 to the power of 3, right? So this is the moment maximum, right? So this is moment maximum. Okay, then we also have the y value, okay, that we have already calculated earlier, right? And also, okay, we have the value of um, I, right? So we have already calculated I value, which is 40.8, okay, times with 10 to the power of negative 4, right? Okay, so therefore, okay, we can calculate this, okay, and we are going to have, okay, our value of the bending stress maximum of 138.9 megapascal, right? Okay, so and since we have a section that is symmetrical on top and bottom, right? So this maximum bending stress is similar on top and also bottom, right? So we are going to have a negative bending stress on top, okay, which is under compression, and we are going to have positive bending stress at the bottom, okay, which is particularly for tension, okay, right? So that is for the maximum bending stress. Then next we move on to the moment of resistance, okay, when sigma is equals to 165. Okay, so as for this, okay, since we have the value, okay, of sigma, or the bending stress is 165, so we are going to manipulate the equation a bit, okay, whereas we are going to substitute, okay, the value of the sigma into the equation. So instead of calculating the value of the stress, okay, but now we are calculating the value of moment, right? So by substituting the value of 165 into the equation, so we are going to get the moment value, okay, or the moment of resistance, okay, of 62.6 kilonewton meter, right? Okay, so as you can see here, okay, this is a different version, okay, of the calculation, okay, whereas we can exchange the values a bit, right, so that we can determine the values of the moment of resistance.